Well, this stepper motor has a lot of wires. It has 6, and some stepper motors just have 4, and you always know what to do with the ones that have 4, because the stepper motor has 2 coils, and each coil, of course, is a wire that has 2 ends. So in this case, the black and green, that's one coil, and the blue and red is the second coil. It's like A and B. And they're labeled that way on the controller. So put the first 2 in A, put the second 2 in B, and it'll spin. We have the same colors on this motor conveniently, so we still know what to do. We can group them, black and green, and red and blue. We got these other 2 wires. What do? We just cut them off or something? You actually could. They'll work just fine with this hooking it up just like the other one. But what are they there for, really? All right. Well, you gotta imagine if you had inside the motor 100 turns. So it goes through the green wire into the motor, and then there's copper wires. And say there's 100 turns between the green and the black. And we're going to measure the ohms between those two. First of all, to prove that there is a coil between them. So I'm just touching one side with each probe of the meter, and it says 8.5 ohms. Okay. So the coil is 8.5 ohms. Well, what they did is they did 50 turns, and then they attached the yellow wire, and then they finished off and did the other 50 turns. So the yellow wire is halfway in between the green and the black. So when we measure between green and yellow in the middle, we should see about 4 ohms, because that's half of 8. That'd be 4.5, something like that. Okay. And we'll see the same resistance from the yellow onto the end to the black. See about 4.5. Okay. So what this means is if we ditch the green wire, we can energize just half of the coil between the black and the yellow. And likewise, we can ditch the red wire, and the white is the center tap for the second coil. So we can energize half of the second coil between the center tap and one end. So why would you do this? Well, what you'll find is that on this motor, when you run it standard like this with the center taps hanging, I'm able to spin this motor about 1/4 of the speed that I can spin it when just energizing half of the coil. And that's because when the resistance is half, then at the same voltage, twice as much current can flow. So the motor will behave a little bit differently. So what I can do in the next part of the video is wire it up like normal, where they're in their pairs, and we'll use a function generator to start slow, ramp up until the motor stalls. And then we will switch over to using just half the coils, using the center taps, and we'll do the same thing, and we'll see what happens. Okay, well, I just finished wiring up this stepper motor in the standard way, using the whole coil. And I'll give it some juice. I'm going to start this off kind of slow at 1,000 steps per second. So there it goes. There, that's a little bit better on camera. Let's increase the speed by 0.1 kilohertz. So there's about 2 kilohertz. And so it stopped at 2.3. We'll try again, nice and easy. In fact, now I'll come here and go even slower, a smaller increment. It can't make it past 2.3. Okay, so you'd have to work out what the RPMs are based on the frequency and all that. I'm just going to compare it to what frequency I can spin it whenever I change the configuration. So now I'm going to replace the red wire, which is one end of coil B, with the white wire, which is the center tap for coil B. Alright, so we just ditched the red wire, and now I'm going to replace the green wire with the center tap for coil A. So again, we're running half of the coil. Okay? And we will see how this works. Let's come back to 1 kilohertz. And hold on, I must, looks like that yellow wire kind of popped out. No problem. Okay. That's what I'm expecting. So that's 1 kilohertz. See if we can go to 2. Let's see if we can go to 2.3. So that's where the other one stopped. There's 3 kilohertz. 4, still going. 5, 6, 7. It's really moving now. 8, 9. So 10 kilohertz, that's about 4.5 times the speed of the other one. Okay, so we can't quite get to 11. Now, I'll remind you that even though we're spinning the motor a lot faster, a stepper motor only has high torque when it's spinning slowly. So if I were to try to grab that shaft right now, I couldn't stop it. But whenever it gets much higher than 3,000 kilohertz, it starts losing its torque really quickly. So I'll take it to 4 kilohertz, and I'll just sort of, didn't really take much. So even though the motor's spinning faster, it doesn't have a lot of torque. Here at 3,000, I really can't stop it. Just with, I don't have much leverage grabbing the axle, but anyway. But there's no denying that we were able to get a higher top speed. So if you had a nice acceleration ramp up of whatever machine this is moving or something, you may be able to get, you certainly actually have the potential to move it much faster. Now the alternative is that in the other wiring configuration, the motor will be torqueier. It'll have more torque, even though it can't reach the higher speeds. Alright, well, I hope that this video was helpful in understanding the stepper motor, all the different wires they got. Thanks for watching.